Imagine this: a blinding flash, a wall of fire miles high, the ground shakes, buildings crumble like sandcastles. This is the terrifying power of a nuclear explosion, a force of nature unleashed by science. But how does this awesome and terrifying energy emerge? It all starts with the tiny atom, a universe of energy hidden within. In the vastness of space, nuclear reactions fuel the stars. Our sun, a giant ball of burning hydrogen, derives its energy from nuclear fusion, a process that we've replicated here on Earth. But our efforts haven't been for the betterment of humankind. Instead, we've created weapons of unimaginable destructive power. To understand this awesome force, we must venture into the heart of the atom, exploring the forces that bind it together and the consequences of unleashing them.
Atoms are the building blocks of our universe, tiny particles that make up everything we see and feel. At the center of each atom lies the nucleus, a dense core containing protons and neutrons. These particles are bound together by an immense force, the strong nuclear force, one of the four fundamental forces of nature. Locked within these bonds is an incredible amount of energy, potential power waiting to be unleashed. This energy, hidden within the atom's heart, is the source of a nuclear explosion's devastating power. There are two primary ways to unleash this energy: nuclear fission and nuclear fusion. Both processes involve manipulating the forces within the atom's nucleus, releasing the energy stored within. However, they differ in their methods and the scale of energy released.
Nuclear fission is the process of splitting an atom's nucleus, a fundamental concept in nuclear physics. Imagine a fragile droplet of water, barely held together by surface tension, on the verge of breaking apart. When struck by a tiny particle, the droplet shatters into smaller pieces, releasing energy in the process. Fission works similarly, but on a much smaller atomic scale. A neutron, a subatomic particle, strikes a heavy atom like uranium or plutonium, initiating the fission process. This impact destabilizes the atom's nucleus, causing it to split into smaller atoms, releasing a significant amount of energy as it does. This released energy, though significant on an atomic scale, is only a fraction of the total energy stored within the atom. The energy released is in the form of kinetic energy of the fission fragments and as electromagnetic radiation. However, the fission process doesn't end there. The initial splitting sets off a series of subsequent reactions. The splitting of one atom releases more neutrons, which can then strike other atoms, creating a chain reaction that continues to propagate. This cascade of splitting atoms multiplies the energy release exponentially, leading to the immense power of a nuclear fission bomb, capable of unleashing devastating energy in a very short time.
Nuclear fusion, on the other hand, involves combining or fusing atomic nuclei together. This process is what powers the Sun and other stars. In the Sun's core, the intense pressure and heat force hydrogen atoms to overcome their natural repulsion and fuse together, forming helium and releasing a tremendous amount of energy in the process. On Earth, we've replicated this stellar process in the form of thermonuclear weapons, also known as hydrogen bombs. These weapons are far more powerful than fission bombs. They use a fission reaction to create the extreme temperatures and pressures needed to trigger the fusion of hydrogen isotopes, deuterium and tritium. The resulting fusion reaction releases an even greater amount of energy than fission, making thermonuclear weapons the most destructive devices ever created by humankind.
Section 5. The chain reaction, a cascade of destruction. The true power of a nuclear bomb lies not just in the initial fission or fusion event, but in the ensuing chain reaction that follows. This chain reaction is what amplifies the destructive force exponentially. When an atom splits, it releases neutrons, which are subatomic particles with no electric charge. These neutrons can then strike other atoms, causing them to split as well, perpetuating the cycle. This sets off a cascade of fission events, each releasing more energy and more neutrons, leading to an exponential growth in the reaction. The process continues, creating a powerful and unstoppable chain reaction. Imagine a single domino falling and toppling another, then another, and so on. This visual helps us understand the concept of a chain reaction. The energy released by each falling domino contributes to the overall power of the cascade, much like how each fission event releases energy in a nuclear reaction. This is a simplified analogy, but it illustrates the principle behind a nuclear chain reaction, where each event triggers the next in a rapid sequence. The speed and efficiency of this chain reaction determine the yield of the bomb, which is the amount of energy released. The faster and more efficient the reaction, the more devastating the explosion.
Section 6. The Fireball, a Sun on Earth. The immediate aftermath of a nuclear detonation is a site of unimaginable destruction. The immense energy released heats the surrounding air to millions of degrees Celsius, creating a superheated sphere of plasma known as the fireball. This fireball expands rapidly, vaporizing everything in its path and emitting a blinding flash of light. The fireball's intense heat sets fire to everything combustible within its radius, igniting massive fires that contribute to the devastation. The intense light and heat from the fireball can cause flash blindness and severe burns at incredible distances, highlighting the indiscriminate nature of these weapons. It's a stark reminder of the immense energy unleashed by tampering with the atom's core.
Section 7. Shockwave, the invisible hammer. Following closely behind the searing heat of the fireball is the shockwave. This invisible wall of highly compressed air travels outward at supersonic speed. Think of it as a giant invisible hammer, smashing everything in its path. The shockwave levels buildings, uproots trees, and hurls debris at incredible velocities, turning everyday objects into deadly projectiles. The shockwave's power diminishes with distance, but it can still cause significant damage miles away from the detonation point. The pressure changes associated with the shockwave can rupture internal organs, even in individuals who are relatively far from the explosion. It's a testament to the sheer force unleashed by these weapons and the devastating reach of their effects.
Section 8. The atmosphere's embrace containing the fury. As terrifying as nuclear explosions are, there is a silver lining. The Earth's atmosphere, while seemingly fragile, plays a crucial role in containing the blast's destructive power. The atmosphere absorbs a significant portion of the initial radiation and heat released by the explosion, preventing it from spreading unchecked. The atmosphere also limits the geographical reach of the fireball and shockwave, preventing them from causing global devastation. While the initial effects of a nuclear explosion are localized, the long-term consequences, such as radioactive fallout, can spread far beyond the blast zone, carried by wind and weather patterns.
Section 9. A history of terror and testing. The destructive power of nuclear weapons was first unleashed upon the world in August 1945, forever changing the course of history. The United States, in an effort to end World War II, dropped 2 atomic bombs on the Japanese cities of Hiroshima and Nagasaki. These bombings were unprecedented in their scale and impact. The devastation was unlike anything the world had ever seen. The sheer force of the explosions obliterated buildings, incinerated landscapes, and left a haunting legacy. Entire cities were reduced to rubble and hundreds of thousands of people perished. The survivors, known as hibakusha, faced long-term health effects and profound trauma. The bombings of Hiroshima and Nagasaki ushered in the atomic age, a period marked by both fear and fascination with nuclear technology. This era saw rapid advancements in nuclear science and a growing awareness of its potential for both energy and destruction. The ensuing Cold War between the United States and the Soviet Union saw a nuclear arms race, with both superpowers amassing vast arsenals of increasingly powerful weapons. The threat of mutual assured destruction loomed over the world. Thankfully, the world has not witnessed the use of nuclear weapons in warfare since 1945. Efforts towards disarmament and non-proliferation have been ongoing, with numerous treaties and international agreements aimed at reducing the nuclear threat.
Section 10. The importance of understanding. Understanding the science behind nuclear explosions is not about glorifying these weapons. It's about comprehending the immense power we wield and the responsibility that comes with it. By grasping the principles of nuclear physics, we can better appreciate the devastating consequences of using these weapons and advocate for their control and eventual elimination. Knowledge is power, and in the case of nuclear weapons, it's the power to prevent their use. By educating ourselves and future generations about the science and history of nuclear weapons, we can strive for a safer world free from the threat of nuclear annihilation.
Section 11. Our nuclear legacy. The legacy of nuclear weapons is a complex one, marked by scientific achievement, military strategy, and moral dilemmas. We live in a world where the power to destroy ourselves many times over exists. It's a sobering thought, but one that should motivate us to seek peaceful solutions and work towards global disarmament. The science that unleashed the power of the atom also holds the key to addressing global challenges such as climate change and energy production. It is our responsibility to steer this knowledge towards peaceful and sustainable applications, ensuring that the legacy of nuclear science is one of hope, not destruction.
Now let we understand the atmospheric impact. We will elaborate on the reason why the atmosphere doesn't ignite, including oxygen, concentration, heat dissipation, and conditions required for combustion. We will include examples of fast nuclear tests and their outcomes, highlighting the lack of widespread and fire in the atmosphere. So now let's get started.
In the heart of a nuclear explosion lies a paradox. Unimaginable power unleashed from the tiniest particles, the very building blocks of matter. This is the realm of atoms, where fission and fusion, two sides of the nuclear coin, hold sway, each with its own unique and powerful characteristics. Fission, the splitting of heavy atoms like uranium or plutonium, is the process harnessed in the first atomic bombs, releasing energy through the breaking of atomic bonds. Imagine a single drop of water releasing the energy of an entire city's power grid. That's the potential of fission, a process that can power cities or devastate them. Fusion, on the other hand, is the power of the stars, the very process that fuels our sun and countless other stars in the universe. It involves fusing light atoms like hydrogen into helium, a process that occurs under unimaginable pressure and heat, conditions found naturally in the cores of stars. The sun, our very own star, is a giant fusion reactor, bathing us in its life-giving energy, a constant reminder of the power of fusion. Both fission and fusion release tremendous energy, primarily as heat and light, transforming matter into pure energy. This energy, when unleashed in an instant, creates the terrifying spectacle of a nuclear explosion, a force of nature harnessed by human hands. But there's a crucial difference between these processes and a conventional fire, which we encounter in our daily lives. Fire needs fuel, oxygen, and heat to sustain itself, a delicate balance that can be disrupted. Nuclear explosions, while generating immense heat, don't rely on oxygen in the same way, making them fundamentally different. This fundamental distinction is key to understanding why the atmosphere doesn't ignite in the wake of a nuclear blast, a crucial factor in the science of nuclear reactions. The most iconic image of a nuclear explosion is undoubtedly the mushroom cloud, a terrifying yet strangely beautiful spectacle that has come to symbolize the destructive power of nuclear weapons. At its heart lies the fireball, a sphere of superheated air and debris that expands rapidly after the initial blast, creating a scene of unimaginable energy release. Temperatures within the fireball reach millions of degrees Celsius, hotter than the surface of the sun, making it one of the hottest phenomena known to humanity. This intense heat vaporizes everything in its immediate vicinity, creating a zone of utter devastation where nothing can survive the initial impact. But the fireball's reign is short-lived, lasting only a few moments in the grand scheme of things. As it expands, it rises rapidly, like a hot air balloon, drawing in cooler air from the surrounding atmosphere, which fuels its upward movement. This influx of cooler air, combined with the rapid expansion itself, causes the fireball to cool quickly, losing its intense heat. Within minutes, the once blindingly bright fireball dims, its heat dissipating into the vastness of the atmosphere, leaving behind a haunting reminder of its brief but powerful existence. This rapid cooling is another reason why a sustained firestorm, while horrifically destructive in the immediate blast zone, doesn't engulf the entire atmosphere, preventing a global catastrophe. Fire, in all its destructive beauty, is a delicate dance between fuel, heat, and oxygen. Our atmosphere, a life-giving cocktail of gases, contains roughly 21% oxygen. This concentration is ideal for life as we know it, but it's not enough to sustain a global inferno. Think of a campfire. You need to constantly feed it wood and provide ventilation to keep the flames dancing. Similarly, a nuclear explosion, while initially generating immense heat, doesn't create a sustained source of fuel or a mechanism to continuously supply oxygen at the necessary concentration to ignite the entire atmosphere. The immense energy released by a nuclear explosion doesn't just dissipate as heat and light. It also generates powerful shock waves that radiate outward at supersonic speeds. These shock waves, like invisible walls of compressed air, are capable of crushing buildings and leveling entire forests. But they also play a counterintuitive role in preventing a global firestorm. As the shock wave expands, it compresses the air in front of it, creating a high-pressure zone. This compression effect, while momentarily increasing temperature, also disrupts the delicate balance required for sustained combustion. Think of blowing out a candle. The rapid rush of air, while containing oxygen, disrupts the flame and extinguishes it. Similarly, the shock wave from a nuclear explosion, while fleeting, creates a momentary disruption in the atmosphere that hinders rather than promotes widespread ignition. Section 5. Echoes of the Cold War Lessons from a Nuclear Past. History, despite its often tragic course, provides valuable lessons.
The Cold War, a period of intense geopolitical tension, saw hundreds of nuclear tests conducted, mostly in remote areas or high in the atmosphere. These tests, while ultimately detrimental to the environment and human health, offered a grim glimpse into the power of nuclear weapons.
They also provided valuable data that confirmed the scientific understanding of nuclear explosions. None of these tests, even the most powerful ones, resulted in the atmosphere catching fire. This empirical evidence, gathered at a significant cost, underscores the fact that even the most destructive nuclear weapons lack the capacity to ignite the atmosphere. Section 6. Forging a Safer Future. Implications for Disarmament and Energy. Understanding the science behind nuclear explosions is not merely an academic exercise. It is a crucial endeavor that impacts global security and stability. It has profound implications for how we manage these powerful forces, ensuring they are used responsibly.
The knowledge that nuclear weapons won't set the atmosphere ablaze should not be a source of comfort, but rather a stark reminder of their destructive potential. The devastation they cause is unparalleled. Our efforts should be directed towards disarmament, ensuring that these weapons are never used again. This is a collective responsibility we must all share.
On a more hopeful note, the same science that underpins these devastating weapons also holds the key to a cleaner energy future. Fusion power, the holy grail of energy production, promises clean, safe, and nearly limitless energy. By harnessing the power of the stars, we can break free from our dependence on fossil fuels and mitigate the threat of climate change. This transition is essential for a sustainable future. Section 7. The Cosmic Perspective, Nuclear Explosions, and the Universe. To truly grasp the significance of nuclear explosions, we must adopt a cosmic perspective.
Our universe is a vast and violent arena where stars explode with the force of billions of nuclear weapons. Supernovae, the cataclysmic deaths of massive stars, dwarf even the most powerful explosions humankind has ever created.
Yet amidst this cosmic violence, life persists. Our very existence is a testament to the universe's ability to create and destroy, to find balance amidst chaos. Nuclear explosions in this grand cosmic narrative are but fleeting sparks, a testament to humanity's ability to unlock nature's most powerful forces, for better or for worse. Section 8. A Legacy of Fear, a Future of Understanding, Public Perception and Nuclear Technology. The shadow of the mushroom cloud looms large in our collective consciousness. The horrors of Hiroshima and Nagasaki serve as a stark reminder of the devastating power we unleashed upon the world. This legacy of fear is understandable, even necessary, but it should not paralyze us. We must strive for a future where understanding replaces fear, where knowledge informs our decisions about nuclear technology. Education is key. By fostering scientific literacy, we can empower individuals to engage in informed discussions about nuclear weapons, energy, and the future of our planet. Section 9. Beyond the firestorm, the enduring threat of nuclear weapons. While the prospect of a nuclear firestorm engulfing the atmosphere is a myth, the threat posed by nuclear weapons remains all too real. The destructive power of these weapons extends far beyond the immediate blast zone.
Radioactive fallout, contamination of water and soil, and the long-term health effects of radiation poisoning are all grim realities we must confront. The humanitarian and environmental consequences of a nuclear detonation are staggering and would reverberate for generations. To view nuclear weapons solely through the lens of a global firestorm is to miss the true extent of their devastating potential.
Section 10. A call for reason in an irrational world. The urgency of nuclear disarmament. In a world often driven by short-sighted self-interest and geopolitical maneuvering, the pursuit of nuclear disarmament might seem like a naive ideal. But the stakes are too high to succumb to cynicism or despair. The continued existence of these weapons of mass destruction represents an existential threat to humanity.
We must work tirelessly towards their elimination. This requires international cooperation, diplomacy, and a shared commitment to a future free from the specter of nuclear annihilation. The alternative is too horrific to contemplate.
Section 11. Our shared destiny, safeguarding humanity in the nuclear age. We stand at a crossroads, the future of our species hanging in the balance. The knowledge we possess about nuclear technology can lead to both our destruction and our salvation. The choice is ours to make. We can choose to cling to the destructive legacy of the past, or we can forge a new path, one guided by reason, compassion, and a deep understanding of the forces we have unleashed. The quest for a world free from nuclear weapons is not a utopian dream, it is an imperative for our survival. Let us choose wisely, for the fate of humanity hangs in the balance.